All right, hi class. So, ready to look at section 212 in mathematical literacy. So with this, we want to focus more on equation solving, and here it's called a state of equality. So really, the purpose of this section is just to, help you understand that we have to add the same thing to both sides, or subtract the same thing to both sides, or multiply the same constant to both sides, or divide both sides by the same number, right? Because those operations will help keep things balanced and keep our scale balanced, right? So just another way to kind of model solving an equation, we can look at solving an equation with like these scales, right? So if you notice, like for example, the number one here, um, we're asked to determine the weight of a small box if the scale shown here is balanced, right? So the idea is each of these small boxes are all the same weight, and we're trying to strategically think through how can we figure out the weight of a box, right? So obviously, if the this is kind of like a teeter totter, right? It's called a double beam balance, right? So if the double beam balance, or if you want to think about it like a teeter totter, if the scale is balanced, right, then that means both sides are equal. Both sides have the same weight on them, right? So the idea is, for example, if I want to get rid of 4 boxes on the right, right, if I want to get rid of these boxes and just leave the weights on this side, I have to get rid of 4 boxes on this side as well, right? So like my new picture, right, my new picture would look like this. So I have 2 boxes on the left, and we would have, the the 3 4-pound boxes, and then the 1 3-pound box left, right? So in other words, on this side, there's a total of what, 15 pounds, right? 4 plus 4 plus 4 plus 3 is 15, right? And then on this side, we have 2 of them. So if I were to take away one of these boxes, I need to take off half of this weight, right? Because there's 2 boxes equal 15 pounds. So if I left 7.5 pounds on this side, then we'd be left with, 1 box equals 7.5 pounds, right? So that's what will go here. Right, so that's just to help us get to thinking what we're going to be doing in this section. So as we work through this section, the 3 questions we want to be able to answer and be thinking about is 1, do you know when to perform an operation on both sides of an equation? And 2, can you tell if an equation is an identity, a contradiction, or neither? And then also, do you have a strategy for solving equations? Right? So we want to focus on these linear equations, or degree 1 polynomial equations, right? So that's what this box is just helping us identify. This is what a typical like linear equation looks like. And A, B, and C are just numbers, and we want to try to solve for x, right? So we want to try to break it down and figure that out. And then there's some examples, right? Like these 2 are linear equations, right? Because I could rewrite it in this form, but this one is not, right? Because it has an x 2 in the exponent. Right, so that's a degree 2 polynomial, right, not a degree 1. Right, and in the last section we looked at, briefly just what a polynomial is. So then with problem 2, what we want to be able to do is solve each one-step linear equation, right? So we're going to do just just through one operation we can get x by itself, right? So in general, if you have an equation in this form where you have a number times x equals some other number, what you're going to do is just divide, by whatever number this is, right? Maybe I call it this number 1 just so you can separate these, right? So number 1, number 2, meaning these are different numbers, right? So if you have a number times x equals a number, you're just going to divide both sides by whatever number is being multiplied by x, right? So like part A, we have negative x equals 7. Well, that's the same thing as negative 1 times x equals 7. Right? I can rewrite negative x as negative 1 times x. So then I need to divide whatever is being multiplied by x. Right? So I get x equals, and then 7 divided by negative 1 is just minus 7. Right? So we get that as a solution for part A. Part B, same idea, right? Negative 5/7 x, right? This is understood that as times in between, right? So if I want to get rid of, whatever is being multiplied by x, this coefficient, I just need to divide by that entire thing to both sides. Whoops, that should be a 7, right? Negative 5/7. So then if we simplify this, right, so of course on this left-hand side, these are just going to cancel out, right? In other words, reduce down to 1, because negative 5/7 divided by negative 5/7 is just 1. Whenever you have the same number on the top, same number on the bottom, right, and you're dividing, it's just going to be 1. So we would be left with just x on the left-hand side. So x is equal to 9 divided by negative 5/7. Right, and of course, with fractions, this would be the same thing as 9 times, and then the reciprocal, so negative 7/5, right? We need to interchange the numerator and denominator. And, with 9, I could write it as 9 over 1 if you'd like, and then you just multiply straight across, right? So x would be 9 times negative 7 all over 1 times 5. Right, which would be negative 63 over 5. So negative 63 fifths, right, would be equal to x. So we have that, right? So that's negative 63 fifths, right? Try to write it a little better here. Right, so the next two are similar, except we have x plus some number essentially equals another number, right? So whenever you have, x plus some number, and I'll say number 1, and this is equal to some other number, I'll call it number 2, then we just want to get rid of, undo this part. So subtract number 1 from both sides, so that way we're left with, what the answer is, which would be, number 2 minus number 1. Right, and then these numbers we would know obviously, and we could find what x is. So similarly, like part C, I have a number plus x equals negative 8. Well, I want to get rid of this guy, right? This 15. So I just need to do the opposite and subtract 15 from both sides, and I'm left with x equals so negative 8 minus 15 is what? Negative 23. Right. So then, of course, we could plug this back in for x, right, and make sure, just like we could with any equation, just to check and make sure that's right? And I'll leave that up to you if you'd like to, but it'll work out, right? So then part D, there's two different ways you could think about this. I think probably the easiest way is to simplify this part, right? So when we have x minus negative 6 equals 20, I would go ahead and just simplify that, because minus a negative, this is just the same thing as x plus 6. Right? Whenever you have minus a negative number, that's the same thing as adding. So this is equal to 20. Right? So then now I just need to subtract 6 from both sides, and we're left with x equals 14. Right? So that's one way to do that problem, as I think about it. A second way that you could have done. So we have, let me just get a little more room. So we have x minus negative 6 equals 20. So another line of thinking is I have x minus a number equals 20. So instead of minus, subtracting, I want to add that same number to both sides. Right? So, adding, subtracting the same number, that's just going to cancel each other out on the left side. So you're going to be left with just x. Right? And then here 20 plus negative 6 is the same thing as 20 minus 6, which is 14. Right? So we get the same result both ways. Right? So the first way we simplified first and then did a one step to solve the equation, where the second way I was just showing you how you could think about it the same way, but just doing it in one step. Right? So without simplifying first. Right? So then now there's some reading here that you can read through. It's just talking, like relating an equation back to its picture and how they can relate to one another. So I'm going to work through an example that does something similar, right? So if you have the equation 4x plus 1 equals 9, right, I can model it with this balance, right, where the boxes are represented as 4x. So if I have 4x's, I have 4 boxes, right, that you see here. So we have 4x plus 1, so I need a additional weight. And then where this fulcrum is, right, on the weight, that's what this thing's called. You can think about that as like an equal sign, right? So if I draw a line here to separate, that's where your equal sign is. And on the right-hand side, I have 9, right, which matches my equation. So algebraically, if I'm trying to solve this equation, right, the first thing that you want to do, and I outlined these steps in the previous video, is to get all your x's to one side and your numbers on the other, right? So I want to move this 1 over here, right? So I could do that by subtracting 1 to both sides. So I'm left with 4x equals 8, right? So that corresponds with this picture, right? And then now what you want to do is, now that you have it in this form where you have, you know, a number times x equals some other number, you just want to divide by the number being multiplied by x, right? So then we're left with x equals, so 8 divided by 4 is 2. And that corresponds with this picture, right? And then, of course, we could check it in terms of a picture by looking back up at this picture and putting the 2's in for those empty boxes we didn't know, and then seeing if there's same weight on both sides, right? But in terms of algebraically, right, I could just plug 2 back in and simplify both sides and see if they're equal, right? So we need to do order of operations, right? So I would multiply before I add, so this would be 8 plus 1, and then 8 plus 1, of course, is 9, and 9 does equal 9, so we get the same result on both sides, so it checks out, right? So then this next thing is, if you remember back in, I forget what lesson it was, where we talked about folding a letter. I think it was like 2.9. Yeah, 2.9. So if you look at page 219 in your textbook, if you remember, we talked about, you know, if you try to send a letter to someone, you know, you'd fold the paper, and then you put the paper in the envelope, and then you would seal the envelope. And then next, we talked about, you know, someone who wants to read that letter, right, has to undo the task, but they do it in a reverse order, right? And we walk through some examples with that, right? So that's just putting this together. It's just helping us think about that. So if you have this equation, right, what are the operations done to x, right? First you would multiply by 4, right, following order of operations, and then you would add 1, right? So when you evaluate an expression, you go, you know, top to bottom, right? But when we try to solve an equation, we're going to go in the opposite order and try to undo each of these, right? So for steps to solve x, the first thing we want to do is undo the add 1, which is subtract 1. And then we want to undo the multiply by 4, which is divide by 4. Right? And this would be a 4. Right? I think I made that worse. Sorry about that. So this is a 4, right? So it's just putting that together. And then let's see, there's a worked out example like we just done. So I'll leave that up to you. You can read over that and double check that. And then I want to move down and try this example, right? So with this example, we have fractions inside of in the equation, right? So a technique that you can do, you know, you could solve it through with fractions just fine, right? But a technique that a lot of students like to do is to what we call clear the fractions. And a way to do that is to multiply both sides by the least common denominator, right? So if I have 2 and 8, the least common denominator between 2 and 8 would be 8, right? So if I multiply both sides by 8, right, you have to multiply the whole side, right? Every term on both sides by 8. What we would end up having is 8 times 1/2 x plus 8 times 3/2 x plus 5/8 x times 8, right? Whoops, that's not a plus there, that's an equals, right? Sorry about that. So that's equals. And then I can simplify each part, right? So 8 times 1/2, right? Half of 8 is 4, right? So this would be 4x. And then, 8 times 3 halves, right? So if you need to, do this off to the side, if I take 8, which is 8 over 1 times 3 halves, right, this would give me, 24 over 2, right, if I multiply straight across. And then 24 divided by 2 is 12, right? So this would be 12x. And then 5/8 x times 8, right? These 8s, you're going to have 8 divided by 8. They're going to cancel out. So you're left with just 5x on this side, right? Geez. Saw another silly error. Sorry about that. This should not have been an x, right? Where it wasn't an x in the beginning. It was just 3 halves. I got a little happy there, I guess. Sorry about that. So I noticed that because everything had an X in it, and I was like, wait a minute, this isn't going to work out, right? Well, I guess the answer would be 0, but I knew that wasn't the case. So sorry about that, right? I just added an X there and shouldn't have. So then now what we want to do is get all the X's to one side, right? So I can subtract 4x from both sides. And those cancel out, so I'm left with 12 equals x, right? Because it'd be 1x. 5 minus 4 is just 1x. So there's my solution, right? So then I could take this answer and plug it in for this x and for this x and see if I get the same result, right? And you should, right? So if you wanted to double check it real quick, let's see. Let me erase around this. I think that's maybe why I added the x in there, is I couldn't see my equation with my writing over top of it. Right? So let me just erase that. So then let me go ahead and just change the color too. So we would have 1/2 times 12, right? Putting 12 in for x. And then we'd have plus 3 halves equals 5/8 times 12. Right, so we want to see what each side equals. Well, 1/2 of 12, right? That's pretty easy to do. That's 6, right? But you could, multiply straight across if you wanted. You'd have 12 over 2, and 12 divided by 2 equals 6, right? So we'd have 6 plus 3 halves equals. So we have 5/8 times 12. So you have 5/8 times 12 over 1, right? So we can simplify this. So in order to add these fractions together, right, we need a common denominator. So I guess I could have just left this as 12 halves, right? So 6 is the same thing as 12 halves plus 3 halves. So now I have the common denominator. And then over here, we would have 5 times 12 all over 8. Right? So on the left-hand side, I could add now, right? This would be 12 plus 3 over 2, right? Which is 5 times 12 over 8. And 12 plus 3, of course, is 15. So this would be 15 over 2. Equals, and then this would be 60 over 8, right? And then the right-hand side, I'm hoping to try to get 2, right? So I'm hoping maybe I can divide top and bottom by 4, and I can, right? Because 60 divided by 4 is 15, 8 divided by 4 is 2, so I get 15 halves over 15 halves, right? So it checks out, right? So I get the same answer on both sides. So that's just a way to check that this is the solution, right? So then with number 5, example 5, we're trying to solve an equation. 4x equals 2 times x plus 1 plus 6 again. And on the left-hand side, they kind of modeled this with the balances again, right? So if you remember the steps to solve an equation that I gave you earlier, the first thing you want to do is simplify if possible, right? And the next thing is you want to get your variables equals your numbers, right, on one side. And then lastly, you're going to divide by the coefficient of x. Right, and then 4, you could check your answer, right? So that's, just a really shorthand list of solving a one variable equation, right? So you want to start by simplifying just to make life easier on yourself, right? So like one way to simplify is if you have to distribute, use distributive property, definitely do so and combine like terms, right? That's part of simplifying. So here we would have 4x equals, so there's nothing I can do on the left-hand side to simplify. But on the right hand, I can distribute the 2 through. So I'd have 2 times x plus, and then you'd have to take 2 times 1, which is 2, right? And then I have this plus 6 still. And then I can still simplify because I can add 2 and 6 together, right? Those are like terms. So I'd have 4x equals 2x plus 8, right? And that goes along with this model, right? So then now what I could do is subtract 2x from both sides. So I get 2x equals 8, right? And that goes with this model. And then I would need to divide both sides by 2, and I get x equals 4, right? Which goes along with this model, right? So notice I went through these steps. First we simplified. Then I moved all my x's to one side and all my numbers on the other. And then I divided by the coefficient of x, right? And I was able to get a solution. And then, of course, we could check our work, right? So if I take 4 times 4, this should equal 2 times 4 plus 1 plus 6, right? So just plugging in 4 into the original equation. On the left-hand side, we get 16. On the right-hand side, you have to do order of operations. Those would be 2 times, so 4 plus 1 is 5, right, plus 6. So then 2 times 5, we'd multiply before we add, so that would be 10 plus 6 equals 16. And then 10 plus 6 is 16, right? So this checks out, right? So so it works out. And then, as I mentioned before, if you'd like, kind of just notationally, you can place a question mark above here along the way because we're testing if it's equal or not, right? It's just we don't only use an equal sign if we know things are truly equal. So that kind of notation is just saying that's what we're testing, right? So I don't think it's a big deal if you don't write the question mark, but just to make that clear and consistent with how the book does it as well, right? So it's just a way to tell your reader, right? So I think, I don't know, at least to me, if I see the word check, like you're checking your answer, it's kind of implying that, but again, it's up to you, right? Math is a language, and you have to learn how to communicate with the language. Right, so then here's solving a simple linear equation. So again, this is somewhat similar to how I did it, but it's a lot more wordy, but it's a textbook, right? So it's going in more details than what I told you, so you could read over that, and if that works for you, great. But if you like my approach, then go for it, right? That's good too. All right, so then the next thing to look at is identities and contradictions. So if you remember previously, I went over in class that there's kind of 3 cases, or not kind of, there are 3 cases when solving a 1-degree polynomial. Right, there's 3 cases of solutions, right, when solving a 1-degree polynomial. The first case is that there's one solution, right? The second case is that you could have no solution. And the third case is that you have an infinite number of solutions. Right, so that's gonna bother me. I didn't put a space here. Let me fix that. Right, so remember how we recognize these is, so let me just make like a table. Oops, need a little bit more space. Here we go. So I'm gonna make a table like how to recognize an example. Right? So I went over this before, but just as a reminder, how to recognize if you have this case with one solution is that you find it. right, you're going to get like x equals 3, right? You're actually going to find what your solution is. So an example of this might be, let's say you have x plus 3 equals 10, right? I could subtract 3 from both sides, and I get x equals 7, right? So I actually find that solution, right? If something has no solution, right, remember what's going to happen is you're going to get a false statement, right? Like you might get, like 5 equals 10 or something like that, right? So an example of this, so just a real easy example, is if you have like x plus 5 equals x plus 10, right? And of course these aren't equal, right? So if I subtract x from both sides, you'll find that I get 5 equals 10, which isn't true, right? It's a false statement. So with the no solution and the infinite number of solutions, like I mentioned before, what should happen is your x variable should end up canceling out, right? Your variable term. That should end up canceling out, and then the difference is with the no solution, you're left with two numbers that aren't the same, and with the infinite number of solutions, it's where you get the same number, right, on both sides. So with the infinite number of solutions, you end up going to get a true statement, like 2 equals 2, right? So an example of this is if you had 3x plus 2 equals 3x plus 2. Right, both sides are going to match, and that's why you have an infinite number of solutions, right? Because if I plug in any x I want on the left side and I'm doing the same thing on the right, then both sides will always match, right? They'll always be the same. So, and of course, if I go to solve this, if I subtract 3x from both sides, then I get 2 equals 2, right? Which is a true statement, right? So that's just a refresher, and the reason why I went over that is because they're using introducing some new terminology, identity and contradictions. So identity has to deal with if you have an infinite number of solutions, and in other words, your solution is all real numbers, right? So remember we talked about how these cases are referring to the number of solutions, the quantity, but that's not necessarily the solution, right? So when you have an infinite number of solutions, your solution is all real numbers, right? So if you have a case 3, x would equal all real numbers. Or another fancy way you can write that is in math we use this boldface R to represent real numbers, right? So x is any number in the real number system, right? So x is all real numbers. And then for the contradiction, that's when there's no solution, right? So contradiction refers to an equation with no solution, and in this case, the solution is the empty set, right? So remember we talked about this as well, and 0, x equals 0 is not even in there, right? The empty set is different than a set with 0 in it. And a fancy way you can show this is through a null value, so you just draw 0 with a slash through it, so that represents the empty set. Right? So then, of course, your solution for the one solution would be whatever the x value is that you find. All right, so we have, let's see, 5 equations left to solve, and then we're done with these notes, right? So let's work through that, right? So the first thing you want to do is simplify for part A, right, or for any equation. So on the left-hand side, I have two like terms being subtracted, 3x minus x. So I can go ahead and simplify that to be 2x, right? And then on the right-hand side, I have 2 times x plus 1 plus 4. Well, let me go ahead and just make this bigger. I guess I don't need the calculator really. All right, let me just make this bigger for us. Right. There. Hopefully that's better. All right. So then 3x minus x, I could just simplify that to be 2x, like I said. And then now to simplify this, I'm going to want to distribute the 2 through. So 2 times x is 2x, and then 2 times 1 is plus 2. And then I would still have this plus 4, right, left over here. So then what this would give me is 2x equals 2x plus 8, right? And then so you should recognize that, so I could put like a plus 0 here. You should recognize whenever you have an equation like this and this number in front of x is the same on both sides, but then these numbers are different, that you're going to get no solution, right? And if you don't recognize that, it's okay, because if you go ahead and solve, if I subtract 2x from both sides, you're going to be left with 0 equals 8, which is a false statement, right? So this tells me that there's no solution, right, to this equation. So what we can say is that the equation is a contradiction, right, using the new term. And the solution, though, right, remember, would be the empty set, right? So the two braces with nothing inside, or we could write the null symbol, right? So this is the actual solution. This first thing, talks about the number of solutions that there are, and then the contradiction is just referring to what the equation statement is, right? So kind of similar to an English class, right? You could make a contradiction, right? Something that you say one thing and then it doesn't actually mean what you're intending it to mean, right? A contradiction. So it's kind of like this in the equation, right? The left-hand side isn't equaling to the right-hand side ever, right? So it's a contradiction, right, in that sense. So then part B, right, again, first thing you want to do is simplify. So we could distribute the 2 through, so I get 2x plus 2 equals 2x plus 2. Right? And again, as soon as you see the same thing on both sides, you should automatically be thinking, wow, this is infinite number of solutions. X can be any real number, right? So, and if you don't recognize that, again, it's okay, because when you go to solve, subtract 2x from both sides, you're going to get 2 equals 2, which is a true statement, right? So there's an infinite number of solutions. So x is equal to any real number, right? X can be any real number that you would like. So it could be pi, could be square root of 2, could be -5, could be a half, any real number, any number on a number line. Right? So then for number 7, it says for each question, state if it is sometimes, never, or always true, and explain your response, right? So for the first one, we could go ahead and just solve for x. So if I add 7x to both sides, I would end up with, 5 equals, this was add 7. Sorry, that's kind of sloppy. Add 7x to both sides. So 9x plus 7x would be, 16x plus 24, right? So then what we could do next is subtract 24 from both sides, right? So that way I don't write on the next problem. I'm just going to recopy this, right? So we could subtract 24 from both sides. And so 5 minus 24 is -19 equals 16x. And then I could divide both sides by 16. Right, and that gives me with x equals -19 over 16. Right? So in terms of what we would say for part A, we would say this is always true. Or no, excuse me, not always true. My bad. I don't know why I was thinking that. So what we're trying to see is if it's sometimes true, never, or always true, right? So the sometimes true, of course, would be one solution. The never true would be, that there's no solution, and always true would be that there's an infinite number of solutions, right? It's true no matter what we pick. So this would be sometimes true, right, for part A. So, you could say something like, when x equals -19/16, the equation is true, but for other values of x, it is false. So the equation is sometimes true, right? So that makes sense, right? It's only true for one x value, so it's only sometimes true, right? So then, since these are kind of close together, I'll just change the color between each of these. So similar thing here, right? With part B, we want to solve the equation. So I want to multiply -2 through to simplify the left-hand side. So that would be -10x plus 30x minus 12, right? And this would be equals, and then I could go ahead and add those two terms together. That would be negative 12 plus 20x. And then I could simplify these two terms on the left-hand side. So that would give me 20x minus 12 equals negative 12 plus 20x, right? And you should be able to recognize, there's a thing called the commutative property of addition. So commutative property of addition, right? And all this just states, it's just a fancy way of stating that if you add two things in different order, it's the same answer, right? So like, if you take 10 plus 6, that's the same thing as 6 plus 10, right? And that's always always true, at least in the real number system, right? Which is that's what we're dealing with. So in other words, what that means is I can change the order of these two things and rewrite this as 20x minus 12 equals 20x minus 12, right? So my point is you should be able to recognize that both of these things are equivalent, right? Both sides are the same, right? So immediately you should be thinking there's infinite number of solutions, right? Because no matter what x I put in, both sides are going to be the same. So this would be always true, right? And x would be any real number, right? Let's see. This was different answer. I don't want that red to run together, right? Should be a line there, right? So maybe a statement you can make, an argument, right? Explanation is you could say if the left side is simplified, it is the same as the right side, right? So since the equation is an identity, it's always true, right? So that's just another term we can use about that equation. That's an identity, right? And that happens when it's always true, or there's an infinite number of solutions. X equals all real numbers, right? And then this part C, right? What you'd recognize when you're solving this is if I subtract 3x from both sides, you're going to get negative 2 equals negative 5, right? So immediately, since that's a false statement, you should be thinking that there's no solution. Oops. I said I was going to pick a different color. Let me grab a different color. I just hate for all this to run together. I'll just do blue. Right. So what I did was subtract 3x from both sides and got negative 2 equals negative 5, which is false, right? So there's no solution. So remember, that means that this equation is a contradiction and that x equals the empty set, right? Or we can show it with the null value, the 0 with the line through it. Right, so in terms of sometimes, never, always true, we would say that it's never true. Right, and then if you wanted some statement to back it up, you could say that the number negative 2 isn't the same as the number negative 5. The equation has no solution, so it's never true. Right, it's just a sample argument that you can make for that. All right, so that's all there is for this section. I'll see you guys later.